Good morning, ladies and gentlemen. My name is Vinay Suramaneni from grade 11 IB of Bangalore International School, and these are my partners Sean Moses, Ruhan Bhatta, and Minjay Kim. We were tasked with researching on the topic of quantum cryptography and creating an experimental design in relation to the topic. What we present to you today is the amalgamation of all our research.
What we'll be discussing today are the basics of quantum physics, quantum mechanics, the idea of quantum cryptography, and the idea of quantum key distribution, as well as the theoretical design that we made ourselves. So let's start off with the basics of quantum mechanics. Quantum mechanics is a subfield of physics that describes the behavior of particles, such as atoms, electrons, photons, and everything else that exists in the submolecular level. The particles that apply to the classical world do not apply to the quantum world. For example, we have the idea of superposition. The fact is that objects do not actually exist in a specific location, and it instead exists in a haze of probability, which basically means that an object can exist at A, but also have a possibility of existing at B, which means that we will not know where it actually exists until we have actually measured the system. We also have the wave-particle duality, which is proved by Einstein and which is proved collectively by Einstein and a lot of other scientists. The fact is that Einstein proved to us that electromagnetic waves, which we call light, exhibits particle-like properties with the photoelectric effect, which is basically when electromagnetic radiation hits the surface of a metal and the photon causes a displacement of the metal electrons, and a photoelectron is born. And we all know that light behaves as a wave, as was shown by the double slit experiment in 1801, which basically means that light can behave as both a wave and a particle, and however, it cannot do so as both at the same time. Now, what are photons? Photons are discrete bundles of electromagnetic energy. They are massless and travel at the speed of light, and each has its own momentum, energy, and speed. They are electrically neutral and can be destroyed or created by the emission or absorption of radiation. And each of them have a specific frequency and wavelength, and thus can be divided into 6 different types in accordance with the range of the electromagnetic spectrum. Now I'll be passing it on to Sean for quantum cryptography.
All right, so the first question I want to ask is, what is quantum cryptography? Now, we know that cryptography is a process of protecting data that is sent across the internet using mathematical processes in order to encrypt data so that it does not get leaked or used for unethical purposes by the wrong receiver. Now, quantum cryptography depends on physics as its mainstay. Through physics, we see that quantum cryptography is able to take encryption to the next level, as it is completely secure against interception between a sender and receiver. This puts intrusion of data being sent out of the question, as the two users are notified if there is any problem. Now, the idea behind quantum cryptography. The physics behind it lies in the use of photons, which are particles of light, to help transmit data over the web through fiber optic cables. The photons are what represents bits, and the whole process relies on the properties of quantum mechanics, which includes the fact that particles are able to exist in more than one place at the same time, particles as a whole cannot be copied, and quantum properties are not able to be observed without changing or disturbing the particles. These properties are what enables interference of data to be impossible, as you cannot measure the quantum state of the system without disturbing the system itself. Now, why are photons used in quantum cryptography? Photons stand as a perfect candidate to be used in quantum cryptography, as they meet all the requirements needed, which are their behavior is understood by us, and due to this, they are easily available to us and are easy to harvest. They also have the ability to carry information through fiber optic wires. Now, I'm going to talk about some of the real-world uses and examples of quantum cryptography, which include Toshiba Corporation, who worked in conjunction with the University of Cambridge and successfully made a quantum key distribution system with the use of the BB84 protocol for quantum cryptography. Boston University, Harvard University, and IBM Research were able to develop the 10-node quantum key distribution network for the Defense Advanced Research Projects Agency Quantum Network, and this project ran from 2001 to 2007. Toshiba, ID Quantic, Quintessence Labs, Magic Q, and other commercial companies were also able to develop the quantum key distribution systems, which they made commercial. Now, some of the benefits of quantum cryptography. There are several advantages when it comes to quantum cryptography, which are a secure connection is established as a use of quantum mechanics, which work on the laws of physics, provides an encryption method that is intricate. It discovers intruders or any third parties that attempt to read the data by changing its quantum state, which adjusts the results. And security is provided in many techniques as there are numerous different protocols, which may also combine classic cryptography to achieve a strong encryption. There are also some limitations of quantum cryptography, and these include error rates that increase with changes in polarization while the protons are in transit. Quantum cryptography uses endless amounts of fiber optic cables and repeaters, which are a large expense and require their own infrastructure. The number of destinations that keys can be sent to are limited to just one, and also the maximum range for quantum cryptography, as we know today, lies only between 400 to 500 kilometers, and this is what causes restriction. I'll now pass it on to my friend Minjay for to talk about quantum key distribution.
In this slide, I'm going to address what quantum key distribution is and the properties of quantum mechanics used to achieve its purpose. Quantum key distribution is a method of transmitting classified information between two parties, commonly referred to as Alice and Bob. It utilizes various unique properties of quantum mechanics such as superposition, entanglement, and Heisenberg uncertainty principle. Superposition is the ability of quantum system to be in multiple states at the same time until it is measured. The quantum computer, unlike the classical computer, uses qubits which can coexist as 1 and 0 at the same time. Quantum entanglement means that the aspects of one particle of an entangled pair depend on the aspects of the other particle, no matter how far apart they are or what lies between them. Also, the properties of one particle will change and affect the properties of the other linked particles as well. Their properties such as spin are complementary to each other, meaning that if one particle has a spin up, the other will have a spin down. Heisenberg uncertainty principle states that we cannot measure the position and the momentum of a particle with absolute precision. Now I'm going to walk you through a brief introduction to the BB84 protocol. It uses polarized photons to transmit data in the form of qubits over a fiber optic cable between two recipients. Encryption keys are sent as qubits, and it serves as a beat, implying it can exist as 0 and 1, and both states can be superposed at the same time. Vertical polarization and horizontal polarization define 0 and 1 respectively, while diagonal transmission axis plus 45 and plus 35 plus 135 can also be represented as 0 and 1 respectively. For example, initially Alice randomly chooses a basis between the rectilinear basis or the diagonal basis for encoding a beat. Bob also chooses a basis for measuring each qubit at random, and he will receive a random result for each qubit he measures since he doesn't know which basis Alice used to encode each qubit. Bob will receive the right beat value with the possibility of 100% from his measurement if Alice and he utilize the same basis for a particular qubit. The likelihood that Alice and Bob share the same qubit will drop to 50% if they each selected a different basis. Any attempt to measure a qubit will necessarily disrupt its quantum state, and hence any eavesdropping attempts will be detected by Alice and Bob, as it will reduce the possibility of Alice and Bob having the same bit value.
Now I will talk about the experimental design. As Sean rightly pointed out, traditional quantum key distribution in quantum cryptography requires a lot of infrastructure, including extensive Ethernet cables, receivers, and retransmitters, which transmitted back along the Ethernet cables. This also presents complications when it comes to distance, because the current maximum range is 100 to 200 kilometers, and it cannot be done when the object you are trying to transmit the data to is moving. To propose a solution to this, we have suggested the theoretical idea of transmitting the quantum key and the following qubits to a satellite in low orbit, which will then transmit it to another satellite, which is also in low orbit, which can then transmit to a receiver on the ground. This is a diagram for you to see. Now, The satellites will read the polarized light photons, and then it will either repolarize them or pass them on with the same polarization, which greatly increases the security while also providing a range of distribution that would have previously been unavailable with traditional Ethernet cables. This provides itself as an alternative to traditional Ethernet transmission, optic fiber transmission. The pros: the data moves faster in a vacuum, such as the vacuum of space, rather than a traditional medium such as air. Additionally, the range will greatly be increased, as I previously mentioned, and since it will be encrypted maybe multiple times by each satellite it has passed through, there will be absolutely no chance of a eavesdropper known as Eve to be able to understand the data that is being transmitted. Thank you.